I forgot to turn this in on Tuesday. I sent you an email about it. They had me sign in on court too.
Oh, okay.
Carol?
Oh. Today is another busy day of lectures. Just as a reminder, we have this lecture plus then in at during lab, we'll be in room 105 where we'll have lecture. So that is today. And what we're going to do this morning is we're going to talk about bond length, bond strength, bond polarity. And then this afternoon or this morning, basically during lab, we're going to talk about molecule shape, molecule polarity, and hybridization of the central atom, as well as bond. I will bring up bond type today, and then we'll talk about it more during lab as well. So a busy day talking about the bonds in a molecule and then talking about the molecule itself. Before I get started, I just wanted to make the announcements. Number one, if you check Blackboard, you should know you do have a test on Thursday of next week. It will be over naming and everything to do with Lewis structures and shapes of molecules. So it's going to be a pretty intense chapter. I mean, a pretty intense exam. So I wanted to just remind you because you need to start studying for that exam. The next thing I wanted to mention is I've been asked by a couple of individuals, so I'm going to go ahead and mention it now, even though it will show up on Blackboard come closer to time. And that is the week of Thanksgiving. I plan to have class, but I plan to do so strictly using Zoom. So you can join from wherever you are. You won't have to come to the classroom for class that particular day. So again, I will have class, but it will be using Zoom instead of meeting in person. Any questions before I get started? Okay, if not, we're gonna get into today's, the material for this morning, which is going to be this concept of, bond lengths, bond strengths, bond polarity, and bond type. So the first thing is, let's talk about the bonds that we've discussed. At this point, we have discussed single bonds, which consist of two electrons, and it's represented with a single line. We've talked about double bonds, which consist of four electrons, and it's represented by basically an equal sign base or two lines. And we've talked about a triple bond, which consists of six electrons and are represented with a triple line. These are our bonds that we have discussed. Now what we want to do is discuss how the length and the strength are impacted by the type of bond that you have. The first one that I'm going, but there is one more thing before we can get into bond length and bond strength that we also need to bring up. And that is going to be a reminder of atomic size, because atomic size also will come into play. And as a reminder of atomic size, the size decreases across a period due to increasing Z effective, and the size increases down a group due to the addition of more and more shells, more and more principal quantum numbers. Whether it's a single bond, double bond, triple bond, as well as the atomic size of the atoms in the bond, those are going to both affect bond length and bond strength. Now, before we get, so let's get into bond length. What is bond length? Well, it's the distance between two atomic nuclei. Basically, the distance between the nucleus of two adjacent atoms. Now, to help us see this, let's just talk about our halogens. If you'll recall, halogens are diatomic elements. So we're talking about F2, CL2, BR2, I2. And let's look at those to help understand bond length and how atomic size impacts bond length. So with fluorine, fluorine is a fairly small element. And when you have two fluorines together, the bond length and I want to find the exact length so I can put it in here. Oh, they don't have bond length. The bond length for well, I don't have fluorine. I have chlorine, which we'll get to. But you can think about the atomic size. And it's a short atomic size. Then if we move on to chlorine, chlorine's slightly bigger because it's in period 3. And this one has a bond length of 199. The next one in line is bromine. Bromine's going to be even bigger. And therefore, the distance between the two atomic nuclei should be longer. And it has a distance of 228. And finally, you have iodine that we're going to discuss. Which has a bond length of 287. So basically, as you increase the atomic size, you increase the bond length. Because there's going to be a greater distance between the atomic nuclei in those atoms. So this would be the bond length. Let's talk about bond strength. For a chlorine, it has a bond strength of 243 kilojoules per mole. That is the amount of energy that must be added to break the bond. For bromine, it's 193 kilojoules per mole. And for a iodine, it's 151 kilojoules per mole. So we said if we increase atomic size, we increase the bond length. Now, what can we say? Right, if you increase the length, then the bond strength decreases. Meaning that they're inversely related to one another. So now that I'm not trying to write and find and draw and everything, let's just review what I've just said. Basically, what I did is I came up with the halogens, which are diatomic elements. And if you look at the halogens from the atomic size, their atomic size increases because we're increasing the principal quantum number, that we're increasing the shell. So the size of those atoms are larger as you go down the group. Because the size of the atom is larger as you go down the group, the distance between the atomic nuclei is longer as you go down a group. Because the distance between the atomic nuclei is longer, it is easier to break. Folks, let me give you an example of that maybe you can relate to on this. Let's talk about sticks and breaking sticks. And I'm talking about the exact same, I'm talking about the exact same diameter of a stick here. You got a really small one and you got to try to break it. Well, you don't have any way to break it, Barry, except with your hands, because it's such a short stick. But as you get longer and longer, you can also use your knee. And you can break the stick with by pulling against your knee. It makes it easier to break that stick. Same thing goes with our bonds. The longer and longer the bond gets, the easier it's going to be to break. So bond strength, by definition, since I did not give that one, is the energy required to break a bond. This can also be referred to as the bond dissociation energy. It is a positive value because energy must be added to break the bond. So we've talked about how atomic size impacts it. Let's talk about the type of bond. Yes.
The bond strength, bond strength and bond, length, how would that look on tests?
So I'll give some examples after I go over the next part.
Okay.
So it's coming. Okay, let's look at the next type though. Because there's more to the bonds than just a single bond. We also have double bonds and triple bonds. And it's easier to think about strength for these first. Rather than length. So we're going to go back to my stick analogy. I'm trying to break one stick. Then I try to break two sticks of that size. Then I'm trying to break three sticks of that size. What can we say about bond, the strength of it? It gets harder to break. So bond strength, the single bond is weaker than a double bond. And a double bond is weaker than a triple bond. Or in other words, you can look at it as this. So this one is the easiest to break. That does not look right. Whereas this one is the hard to break. So to just demonstrate, to give you an example, carbon, single bond carbon, it's 347 kilojoules per mole of energy. A triple bond carbon, a double bond carbon requires 611 kilojoules of energy to break, whereas a triple bond is 837 kilojoules of energy to break. As far as bond strength goes, or bond length, excuse me, a single bond is longer than a double bond, and a double bond is longer than a triple bond. In other words, folks, these statements I made up here with respect to the bond length and strength, it still fits with a double and triple bond. The longer the bond, the easier it is, the less energy that is required to break it. So what's important? What's the order of importance? First, sort according to bond type. Where a single bond, double bond, triple bond. Single is longer and weaker, whereas a triple bond is shorter and stronger. Then, after you've sorted according to bond type, you sort the bonds based on the atomic size of the atoms that make up the bond. As far as test is concerned, this probably is the take home. Let's look at an example of how it would look on the test. So this is an example of what you might see. Sort the following bonds in order of increasing strength or increasing length. So I'm gonna want the shortest. And then I'm gonna want the longest. The first thing I'm gonna do is sort based off of type. So C triple bond C, let's see, C double bond O, and then all of the single bonds. So all I've done is sort by bond type. Now I can actually go in and sort further. Because I can take these three that are the longest and sort by atomic size. So what I notice is period 2 and 2. This is period 5, 5 and 3. And this is period 1 and 2. Why did I look at periods first? Because they made the most sense to look at, because period is the predominating one. And so just looking at the periods, as far as the shorter one that is left, that is going to be the HF, because it has the smaller atoms, followed by the OF, followed by the ICL. So the latter, what you see at the bottom, is what I would expect on an exam. Questions? Again, I sorted by type of bond first. That's the most important. But I had 3 single bonds. So I then had to sort out those 3 single bonds by atomic size. If you go back to the last exam's material, when it comes to atomic size, the predominating factor is the period number, because that indicates the shell. The higher the shell, the bigger the shell, the bigger the atom. So I sorted by period number. If I'd have had one more in here, say I would have had, or let's say I would have had, yeah, HO, for instance, where would it have fallen in this grouping? Is it, they are both in the period 1 and 1 and 2. Remember, we're going from shorter to longer. So is HO going to be shorter or longer than HF? Huh? Longer. So it would have gone into this location. Because oxygen is slightly larger than fluorine. And because it is slightly larger, it is slightly longer. Questions? Did that answer your question from previous?
Yes.
Now I could do, instead of length, I could have done strength. If I'd have done strength, this would have all been reversed. Because it would have been from weaker to stronger or something. but it's gonna be something along this lines. Now, on active, they don't make you, I don't think they make you do long stretches of things. I think it's usually one or two. But on a test, this is what you can expect. Questions? So I just wanted to show you the diagrams. This is the length strength diagram of HO. There's HO. They don't actually have HF in here, but as you'll see, oxygen was slightly smaller than nitrogen. So its length is shorter. And because the length is shorter for HO, it is higher in energy than was HN. And also here you can see nitrogen is a slightly smaller atom than carbon. So even though these are both the same type of bonds, they're both triple, not that it's that visible, but they are both triple bonds. Because nitrogen is a slightly smaller atom than carbon is, its length is shorter and its strength is greater. Questions? Okay. So we've talked about bond length and strength. Now, as far as these bond strengths, they can then play into other things. For instance, we can talk about the energy needed to break methane into its atoms of carbon and 4 hydrogens. So methane, its Lewis structure is this. When you look up the bond energy, for CH, it is 414 kilojoules per mole. This molecule has 4 CH bonds. So it has 4 times 414 kilojoules per mole. And that's what you would need to add in order to break that methane up, which is 1,656 kilojoules per mole of energy. So we would have to add 1,656 kilojoules of per mole of energy would need to be added to break methane into its atoms of carbon and hydrogen. So when we're talking bond strength, you're not only just talking how strong is the bond, but you're also talking about what type of energy must be added in order to break a bond. And how much must be added to completely break up a molecule. If I were to go with ethane, now we have 6 carbon-hydrogen bonds, but we also have 1 carbon-carbon bond. If I look up their information, a carbon-carbon is 347 kilojoules, and a carbon-hydrogen I said was 414. So when you're looking at the energy, it takes 2,484 kilojoules to break up the carbon hydrogens. And then it also takes an additional 347 kilojoules to break up the carbon-carbon for a total of 2,831 kilojoules of energy. So these bond strengths are also describing how much energy must be added to break up all those bonds in a molecule. Questions? We will probably see this, I hope to see this later on in the semester. So this will not be on this immediate exam, but it will be on future exams. But since we're talking bond strengths, it's important to know what it all means. It's not just how strong is it, it is also how much energy must be added to break it. Okay, so now we're going to get into bond polarity. And to get into bond polarity, you have to understand electronegativity. And folks, electronegativity is not the answer to everything. I know a lot of individuals will like to pull out the word electronegativity when they're trying to come up with an answer, but it's not the answer to everything. Electronegativity simply describes how much time electrons in a bond will spend around an atom in that bond. The higher the electronegativity, the more time an electron spins with that atom. Now, if you remember, electrons are negatively charged. So if they spend more time around a particular atom, a polarity is obtained. Polarity comes from the word polar. It's polarized, with one end being more negative and one end being more positive. Now, there's a couple of different ways that things can be described. But basically, we describe things as nonpolar if the difference in electronegativity is 0 to 0.4. We describe it as being polar if the difference in electronegativity is 0.5 to 1.9. And then it is described as ionic when the difference in electronegativity is greater than or equal to 2.
What if it's like 0.45?
Okay, so I was just asked, what if it's 0.45? If you have an electronegativity table that gives you 2 decimal places, then it's anything up to 0.5.
Okay.
But a lot of electronegativity tables only go to 1 decimal, so, but there are a few out there that go to 2. So. Now, what does this mean? What it means, so when we say something is nonpolar, let's talk about a carbon-carbon bond. When we're saying it's nonpolar, if we look at the, instead of talking in terms of a bond, if we look at its density diagram, where the density diagram describes how much time an electron is spending with a particular atom, what we see is that in this density diagram, it's relatively equal expenditures. No single carbon is going to get more time. Whereas if we talk about something like HF, hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. The difference in this electronegativity is 1.9 is the difference. When we look at the diagram, therefore, of our HF, because hydrogen has such a small electronegativity compared to fluorine, what it means is that the electrons in that bond spend very little time around it compared to the time they spend around the fluorine. Now, because electrons are negative, this creates a polarity towards the fluorines. And it's taken away from the hydrogen. So this is a dipole moment arrow. And it is used for polar molecules. The crossed end of the dipole moment arrow means that that is a partial positive. It's easy to think of because positive is usually written with a plus sign. You got a plus sign there. Now partials, they usually use delta, and my delta looks funny, so I don't usually just draw the delta. But that's what it means. And then the other end is a partial negative. And the arrow is simply showing the direction that that is going. Then let's talk about NAF. Sodium, if I'm not mistaken, has a electronegativity of 0.9. Fluorine electronegativity of 4.0. We're talking about a 3.1 difference here. So basically what we mean is that with respect to our sodium and our fluorine, because fluorine's electronegativity is so much larger, pretty much those electrons spend all of their time around fluorine and none of their time around the sodium. That's where we get the whole idea of Na plus F minus from. Now, folks, it is not as black and white as what we described when we were describing ionic compounds. An ionic bond does not necessarily mean an ionic compound, and an ionic compound doesn't necessarily mean an ionic bond as far as by this definition. So we still talk ionic compounds like we described them to begin with. But an ionic bond is going to use this particular set of definitions by differences in electronegativity. The way it would be asked on a test, number one, you're given your table of electronegativities. And I'll ask, is this bond polar, nonpolar, or ionic? That's all there is to it. You have to, but you have to know. So what do you have to know to be able to answer the test? That. You have to know these differences to be able to answer the test. Okay, the last piece today is bond type. And what I mean by this is, how is the bond formed? The first bond formed between any two atoms occurs through direct overlap of orbitals. These bonds are called sigma bonds. And are represented with the the small Greek letter for sigma. Any additional bonds formed between those same two atoms occur from side to side overlap of p orbitals. These bonds are called pi bonds. And are represented with the lowercase pi. So let's say I have an HF bond. Well, since there's no, the first bond is going to be a sigma bond, so HF has only a sigma bond. I could have methane and every single bond in that methane is going to be a sigma bond because there's only one bond between the two atoms. But if I have something such as HC triple bond N, for the HC, it's going to be a sigma bond. And one of the bonds between the C and the N will be a sigma bond. But the other bonds between those same two atoms, C and N, are pi bonds. So methane has 4 C single bond H sigma bonds. Hydrogen cyanide has 1 CH sigma bond one CN sigma bond and 2 CN pi bonds. You will, again, later today, I'm planning to show some videos. And the videos do a much better job of illustrating what a sigma bond and a pi bond looks like than what I can draw. So you will see two, so we will come back to this point today during the lab timeframe. So today, all I wanted to do was go over the basics: bond length, bond strength. We talked about the bond strength and how that applies to the energy to break a molecule apart, the bond polarity, and then the bond type. The bond type we'll actually encounter in greater detail today in the laboratory when we, or at least you'll get to see it, but it will apply to what we're doing in the laboratory. Now today in lab, it is going to be a long day. Bring a snack, bring something to drink. Because we have got to start, we'll start with the Lewis structures, and I'll teach you how to take the Lewis structure that we developed in class on Tuesday and last Thursday. We'll take the last Tuesdays. We'll take those Lewis structures. We'll then apply VSEPR theory. With the VSEPR theory, we're going to determine the electronic structure or electronic geometry, and then we'll describe the molecular geometry. We will take that molecular geometry and we will look at the electronegativity of the atoms in the molecule and ultimately determine molecule polarity, which is different than bond polarity. And then we will use valence bond theory to determine the hybridization of the central atom. And finally, we'll apply what we just talked about with respect to the bond type to the atoms in the molecule and determine the bond types in the molecule. Make sure that you bring the document that I passed out on Tuesday, as it will help us in getting through the VSEPR, valence bond theory, and so on and so forth. And it's going to be a long one because we're going to do many, many examples. But this is one of those concepts that requires a lot of examples. And so if you've looked at Blackboard at all, there is a list of VSEPR, valence bond. Basically, what I did is there's about 100 and something molecules. Each molecule is a separate video. So you can watch as many videos as you need, but you don't have to watch all the videos. But this concept can be challenging enough that you have 2 lab grades over it, because we will have spent 2 days in lab on this stuff. You have 2 lab grades over it. One is a Blackboard quiz, which is 60 questions that goes to that 25 points. And one is a result of 5 ed puzzles that are related to geometry. Now, do you have to do that before your test next week? No, I've made it due the Friday after the test. But would it be wise to do them before the test next week? Probably, since it's going to be on the test next week. I am forewarning you, this test next week is probably for most students. The way these tests work out, the first test is general information. The second test probably has the most information on it that you have never seen before, because a lot of people don't go into quantum numbers in high school or anything like that. The third test is probably the most challenging test because of the fact that it is naming and VSEPR theory and valence bond theory and Lewis structures, and there is absolutely no place that I can give you partial credit. And the fourth test is usually is the mathematically inclined test, because it's almost entirely math. And so this test can be the most challenging for individuals because of the fact that it's either right or it's wrong. So I'm warning you because you have a week before your test. And you need to start studying for it. Don't wait like a lot of times on this test. Yes.
What all are we gonna be given?
You will be given your periodic table. You'll be given your table of electronegativities. You will be given a formula sheet that does include the formal charge calculation on it. I want to say that's it. Which seems like not a lot compared to what we've gone over. Because most everything is embedded in the periodic table, or it's stuff that you just have to know. I'll do my best to help you memorize it, but still. Questions? The last thing I want to mention is, I don't know if you saw my email that I sent out. If you are going to donate to the Bear Food Pantry, if you want to get it to me by X period today, I'll give you an additional 5 points. Instead of it being worth 10 bonus points, it'll be worth 15 bonus points. But I need to get it by X period today so that we can get it over there. Okay, that's it. You get an extra 5 minutes to go get some Starbucks, which I think somebody told me if you've got the Starbucks app, you get something like half off of drinks after noon. Something like that. Here are the 2 documents from Tuesday.
And then I have to.
Okay.
Should I take it up to your?
Yeah, take it up to my office and just stuff the sheet inside.
The documents from Tuesday. I was guessing. Be in your office.
I will be in there until 10:40, and then I will be in there X period. Otherwise, I'm in lab all day.
How much would you want to donate?
Huh?
Is there a specific amount of food to donate?
It's like 10 items is what yeah, it's usually a point per item. I'm fixing to go up there now, and then I'll be there until 10:40, and then I will be there during X period. That is it. Otherwise, I'm in lab today.
Do we need to bring all 13 items or just 10?
Just 10.
Just 10, okay. Okay, and with the compound and structure, what do you mean by that?
And you can turn that in later.
Okay.
Basically,
okay.
look at the
You just
back of
want
the,
food wrap?
yeah, just look at the back and there's ingredients. You find an ingredient and then you go on Google and find its structure and just
Oh,
draw out the
okay,
structure.
Okay, okay, I'll turn it. I'll just bring this stuff today.
Okay. Yes. Now, some people you can also put it outside my office if I'm not there, just don't block anybody else's door. That's the other problem.